Welcome to the third lecture of the Network-Centric Innovation course. In this lecture I would like to expand on the concept of 6 degrees of separation and show the two most important property of real networks, that is small world and scale-free networks. What is the small world property? The 6 degrees of separation concept indicates that in most real networks the distance to connect any two nodes from far away that they are is relatively small, 6 or less than 6. This is kind of astonishing because in reality we would expect that distance to be much higher for the simple reason that we also pointed out that density in real networks is very low. If density is low, it means that nodes do not have many links, and therefore we would expect the distance between any two random nodes to be high. This is not the case. Why? The small world phenomenon is characterized by two features. Number one, the distance, or better, the number of links to send information between two randomly selected nodes A and B is small, like in the 6 degrees of separation, but at the same time the local density is relatively high, although the overall density is very low. Let me try. In order to understand the small world, we need to understand two concepts: the clustering coefficient and the path length. The clustering coefficient indicates the probability that two networks connected to that share a common network, a common node, are connected to each other. Or better, if you imagine any two of your friends are friends among each other. In a relatively tightly connected network, like say in a village, if we take this node here and if we take 3 other nodes that are connected to the blue node, a network will have maximum clustering coefficient, that is clustering coefficient equal to 1, if these other 3 nodes are connected among each other. In practice, if we call this network this node A and this node C, E and F, and if C, D and F are friends with A, then clustering coefficient equal to 1, it means that these 3 are friends among each other. And this is a situation as described of a tightly connected network like a village. If we're in a city instead, and a person, always the person in blue, has the node in blue, sorry, has 3 friends referring to 3 different networks: the network of work, the network of church, and the network of family, it is likely that those 3 nodes are not friends among each other. Okay, so a clustering coefficient is characterized by the fact that 2 or more people connected by a common friend are friends to each other. Real networks are characterized by the fact that overall the local density, or in other words the clustering coefficient, is high. Then path length. Path length is nothing else than minimum distance. So it's basically the number of steps necessary to send information between 2 randomly selected nodes. In this slide I show 2 examples of small world networks. Small world networks are characterized by the presence of tightly connected subnetworks which are connected with each other by some shortcuts, what we called the weak links weak ties in the previous lecture. Notice that local density is very high, but overall density is very low, and this satisfies the criteria of real networks. Why local density is very high? Because inside here most individuals are connected with most other individuals. Basically, inside my tight circle of friends, 2 of my friends are likely to be friends among each other. This is the idea that clustering coefficient is very high. But if you divide the number of links that this node has with the number of links that this node might have over the entire network, then you immediately understand that overall density is very low. At the same time, because of the shortcuts, the weak links, the weak ties present in this network, the distance between any two selected individuals is relatively low, because you can always bridge the gap by using the shortcuts. This is another example of a small world networks in which the same property is present. This is connectivity within the subnetwork is very high, or in other terms, the cluster coefficient is very high. The path length is low due to the presence of the shortcuts. To understand and analyze small world networks, we use the Watson-Strogatz model. Watson-Strogatz are the two scientists who introduced both the terminology small world and the theory behind it. To develop a mathematical theory, they started from the simplest possible arrangements of nodes and links, that is, nodal links distributed around a circle. Note that this is an ordered network, because the same distribution of links, in this case links connected this node to the 4 closest neighbors, is repeated across the network. This network is clustered because the neighbors of this node are connected to each other. In this case, the cluster coefficient is 0.5 because two of the neighbors of this node are connected among each other. These two are not. Notice that this is a clustered network, meaning the cluster coefficient is relatively high, 0.5. But it's not small world. Why it's not small world? Because the average distance to send information from one node to the other node is maximum. In this case, if I want to send information from this node to this node, I've got to go through three links. So this is clustered, high clustering coefficient, but not a small world. Notice what happens when I rewire. I break some links, say these links, and I rewire this link randomly to another node. What happens? The clustering coefficient on average is still very high, but the average path length goes from 3 to 2, so it decreases of 33%. And this is the property we want to explain. We want to explain how real networks at the same time have got a very high local density. My friends are friends among each other, but at the same time the distance, as I said, the number of links to send information from any two random links is very low. So this one, although it is still a relatively ordered, very ordered network, we have rewired only about 10% of the links. This network is now a small world network. If we rewire all the links, so the disorder of the networks is maximum, now the cluster coefficient is minimum, but of course the path length is minimum at least. So this is a non-clustered but a small world. By small world we mean that the path length is slow. And in this graph we capture the dynamics going from this type of network ordered to a disordered type of network. Notice that this is the ratio of the path length of an ordered network. This is p equal to 0, completely ordered, divided by the maximum path length, which you get at p equals 0. This is the cluster coefficient divided by itself at the value of 0 disordered parameters. Notice how rewiring a tiny percentage, in this case only 1,000th, in this case only 100th of the number of links, the average path length collapses very quickly, but the clustering coefficient remains high. In this area, we have small worlds. In order to understand better small worlds, let me introduce the concept of simulation, computer simulation. What we're going to do in the following is actually to download an open source simulation model. So what I invite you to do is to go to this website, download this simulation program. Simulation program is open source, so it's legal to download and to use it. Once you download it and install it, then click on File, which is there, and select Models Library. Click on Model Library within that menu, and then select Small World. Once you select Small World, you will see this graph, so you will see the distribution of nodes and links typical of a small world Watson-Strogatz model, and you can play with the parameter. I invite you to click on Setup here. Once you click on Setup, you will fill the model with nodes. If you click on Info, then you will see you will see a description of the model, what it does, and how to understand it. If you click on Code here, you will see actually the actual code. Let me show it. So as I said, if you click on Info, you will see a description of the model. If you click instead on Code, you will see the actual code of the model. The coding language is a particularly simple code, that the NetLogo code that you can learn in a few days. This is a program used by students of high school in the United States, and they learn it in 2 or 3 days. Let me show how the models work. Now, we have downloaded we have installed the program. We have selected the small world simulation model. Once you click on Setup, you will see the nodes and the link in this graph. In this case, I have used this slider and increased at maximum the number of nodes. Each node at the beginning is connected only to the 2 neighbors. Okay, so this node will be connected to this node and that node. Now, if you click on this button called Rewire One, you will break one node between two adjacent to neighboring nodes and rewire randomly to another node. So imagine we break this node here and we connect this node now randomly to another node, in this case this one. You can play that several times. In this case I've done it 5 times, and here you can observe how the path length and the cluster coefficient changes. Notice that having rewired 5 times, the cluster coefficient has decreased but marginally, whereas the path length has basically been halved by having rewired a tiny percentage of the total number of links. Here you will get information about the exact number of clustering coefficient. In this case, you get the average path length, which has gone from about 15, this is a ratio, to now about 8. If you click on highlight, then you can see what's happening to any single node. It is represented in the next slide. We can get information about the cluster coefficient and path length of each single node in the simulation by pressing highlight and then clicking on any node on the graph. Let's say we click on this node. This node becomes red. The nodes that become blue are the nodes with which the red node is connected to. Notice that the clustering coefficient is maximum in this case. Why? Because we know that these two adjacent nodes, we are still in the condition of an ordered network, hence these two are connected, and these two are connected. Of course, this is not connected to that one, this is not connected to that one. So if you take the ratio between the actual links and the total possible number of links, you get 0.5. The average path length has gone down from the maximum, which is 15. The average path length is calculated by calculating the path length between any two these nodes and any node and all the other nodes in the network. In this case is 1, between these two is 1, between these two become 2, and so on and so forth. If you take the average, it's 15. In this case it's not 15 because we have introduced some shortcuts. So let's imagine you want to send information from this node to this node here. Here you go, here the path length between this node and this one is maximum, but here suddenly you have a shortcut. So in this case it's 12. Notice if instead you select in the same simulation this node, notice now that the blue nodes are different because three of them will be close as in an ordered network, but the fourth one will be distant. This causes the clustering coefficient to collapse to 0.16, but the most interesting information is about the collapse of the average path length, which goes from in this case 12 to about 7.2, so less than half than the maximum. Why this? Because now this connection dramatically decreases the average path length of the red node with all the others. And this is the magic of the small world model, which explains several characteristics of real networks. What are in real social networks, we have that we have the 6 degrees of separation phenomenon. That is, we can connect any two nodes in a network. It doesn't matter how big, even the network of all people on the planet Earth, billions and billions of people, with only a limited number of links. In the case of 6 degrees of separation, that's about between 5 and 6, and that was 6 before the emergence of the internet. At the same time, in real social networks, we also are densely connected within our close friends or colleagues. So it is from the point of view of a densely connected local networks, is as if we were living in a village where everybody knows everybody else. My close friends are friends among each other. On the other hand, it is also as if we are living in cities, because now we can send information as in cities through to networks through a small number of links.